Hello class, today we're going to continue our intro to logarithmic functions, and today I'm going to focus my attention on some of the properties of logarithms, and you'll later see that these properties carry over to so many different things, and knowing these properties are very important in helping you to simplify expressions and make things easier for you. So from last class, we discovered that if you had this exponential function, a to the x, it had an inverse, and we discovered that inverse was log ax. So I want us to go through these set of properties, these four properties, and make sure that they're sound to you and you can apply it when you see a similar pattern in problem sets. Okay, so the first property says that log a of 1 is equal to 0. So for us to do the proof, let's just get rid of the 0. Let's see if we're going to get that same answer. So we have this log expression here. We know that every log expression returns to us an exponent. So for now, let's just say that this exponent is x. If that's the case, then we can always change a logarithmic expression into its exponential form. So this is the same as you writing this as, remember that a represents the base, the x is the exponent, and then the 1 is the argument. So we end up with a to the x is equal to 1. So the question we can ask ourselves is, if you have a base, any base apart from 1, all right, and you raise it to a power is equal to 1, can you think of an x value that will return me a raised to a certain x value that will return me to 1? And your guess is right. X would have to be what? 0. So indeed, log a of 1 is equal to 0, meaning that if you have any log of it, if you have a log of any base, as long as the argument is 1, the outcome is going to be what? It's going to be 0. This is a fact that you can use wherever you see something similar. So for example, if I gave you log 3 of 1, we know that answer is going to be 0. Let's look at the second rule. The second rule is log a of a, and it says this is 1. And this is very intuitive. From the way we set up logarithms, we said that we are asking ourselves, to what power should I raise the base to give me the argument a? And in this case, clearly it's 1. But let's do the proof. So again, if I take away the 1 and I set this equal to x, then we can see that this is synonymous to me writing this in the exponential form. A to the x is equal to a to the power 1. Well, since we have the same base a, we can compare the powers. So x has to be equal to 1. So we are saying that log a of a is equal to 1. That is a fact that you can carry with you and use anywhere. So for example, if I gave you log 25 of 25, that should be what? That should be 1. So that's the second proof. Let's look at the third proof. So the third proof is log of a to the x. Well, again, this is kind of intuitive too. We're asking ourselves, to what power should we raise a to give us a to the x? Obviously, the outcome should be x. All right, but let's do the proof for that. So again, if I take away this x, we know that every log expression returns us back an exponent. So this is y, because I can use x. I already used x already. So this is going to tell me that this is the same as a raised to the y is equal to a to the x, if I convert it back to an exponential form. Well, clearly I have the same base, and if it's equal, then the powers must also be the same. So we're saying y is equal to x. In this way, we can now claim that log a of a to the x returns us back to what? X. Again, this is another fact that you can hold on to and use. So for example, if I gave you log 7 of 7 to the 2, then this is what? That's just 2. All right, let's look at the last one. So the last rule says that a log a of x is equal to x. Now that is not quite intuitive. So let's see. Let's clearly see what's going on over here. Remember that a is a base. So really this is an exponential form. Where this is the base, that's the base. This whole log expression here is the exponent. So the expectation is that it should return me back an argument. So let's call this argument y. So really, what this question is saying is a log a of x is equal to y. Now let's switch everything back into a log. So if we switch everything back into a log, this is going to become a, well, not a, but log a of y is equal to log a of x. Well, since I have the same log expression, that means that y, the argument y and x must be equal. So y is equal to x. So we can clearly see that a log a raised to log a of x should return me back to x. Again, this is a fact that you can use. So an example is if you have 3 log 3 of 2, we're saying that should return me back to 2. Okay, so let's look at some quick examples and let's see how things work when we use these powers or these properties to solve problems. All right, so my first example is if I have log 3 plus 3 log 3 to the 5, I can clearly see that let's label this as method property 1, property 2, property 3, property 4. Then I can see that log 3 of 3 squared is very similar to property number 3. So that outcome is going to be 2. And then a base raised to a log of 3 of 5, that is similar to 4. So that should return me plus what? Plus 5. So I get what? I get 7. Okay. Let's look at another one where we have log of 15 to the 1 times log 2 to the 2. So log 15 to the 1 is the same as 0. All right, if you look at property number 1. And then log 2 of 2 is an example of property number 2. So that is 0 times 1, which is 0. Okay. If I look at the next example, let's say if I gave you 5 log 5 to the x over log 3 to the 3 plus log 5 to the 25. So the numerator looks like property number 4, so the outcome is going to be x. And then log 3 of 3, that looks like the property number 2, so that gives me 1. Plus, well, log base 5 of 25 is not part of the property, but we understand what a log does. So we are asking ourselves, to what power should we raise 5 to give me 25? That is what? That is 2. So this outcome is just x over what? X over 3. So I hope just messing around with the properties and what we know about a log, we can do so many interesting things. We could add two nice numbers. So for example, I could have given you log, well, I've been using 3 a lot, so let's pick up another base. Log 4 of 16 divided by log 5 of 5 squared plus log 3 of 9 divided by 4 log 4 to the 64. That's too big. Let's make it, say, 2. Okay, so I have a lot going on over here, but really, if we look at everything, look at the numerators and denominators, we can simplify each of them using the properties of what a logarithm means. So to what power should I raise? If I look at the numerator on the left, to what power should I raise 4 to give me 16? That's just 2. And then if I look at the denominator, it says log 5 of 5 squared. What is that equal to? To what power should I raise 5 to give me 5 squared? That is property number 3. That is just what? That's just 2. Plus. Now if I look at the next one, I have 3 raised to what power should that give me 9? And that is also what? That's also 2. And then if I look at the denominator, I got 4, a base of 4 raised to log of base 4 of 2. That's the same as property number 4. That should return me back to what? Back to 2. So really this was 1 plus 1 equal to 2. That's just a cheeky way of writing 1 plus 1. All right. Okay. I hope you enjoyed this. In the next video, we'll look at graphs of logarithmic functions.